Good evening, everyone. Thank you so much for joining us tonight at the public lecture hosted by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. My name is Xin Du. I am the Outreach and Engagement Manager at KIPAC, and I will also be your main host today. It's so wonderful to see many of you here in person, and we also welcome the online group of a similar size who is right now watching the live stream. I can see many familiar faces, and also we welcome the newcomers. So you may have noticed, if you have been following KIPAC for a little while, today's topic is not a typical astrophysics or cosmology lecture that we normally feature. And that's because this topic was selected solely based on the audience feedback. We got a lot of votes for planetary sciences, and we also haven't really featured anything related to exoplanets in the last few years. In the meantime, we also recognize that there has been a tremendous amount of discoveries made in this field of study, especially by the James Webb Space Telescope, or JWST. And we thought it would just be a wonderful timing to actually feature some of those latest results, and especially related to the atmospheres and potential habitability of rocky planets. So before we start, I would like to give a very quick shout out to the entire team who is supporting this event behind the scene. That includes the front desk staff who you have already met during the check-in. We have the tech team supporting us, and we also have Leon who is doing the live stream. And since this is a hybrid public lecture, we also have online chat moderators who are subject matter experts on this topic that will be answering questions online. So before we start, I will give them a quick opportunity to introduce themselves. All right. So first we have Lemona.
Hi, everyone. My name is Lamona. I'm a PhD student in Laura's group, and I'm modeling energetics of core to infer dynamo actions for planets. I hope you guys enjoy the talk today.
Great, thank you. And next we have Andrea.
Hi, everyone. I'm Andrea. I'm a PhD student in Laura's research group. I'm interested in how asteroid impacts affect the evolution of life on other planets. And I'm excited to be here with you all to learn more about the latest development in the field of exoplanetary sciences.
Awesome. And last but not least, we have Michelle.
Hi, everyone. I'm Michelle Hill. I am a postdoctoral researcher with Laura in the EPS department, and my focus is exoplanet habitability and modeling that, and also detecting exoplanets with both ground and space-based telescopes. And I can't wait to answer all of your questions.
Wonderful. So for those of you joining us online, you'll see the live chat box on your right-hand side. Feel free to put in your questions, and we also welcome you to engage in discussions. Most of the questions online will be answered by the chat moderators as they come in, and the remaining field will be saved for Laura to answer during the Q&A. And for all of you joining us here in person, we kindly ask you to save your questions until the very end. We will have a moderated Q&A in the end, and you will also get a chance to ask Laura your own questions once the event has finished. So now it is my greatest pleasure to introduce tonight's speaker, Professor Laura Schaefer. Laura is an assistant professor here at Stanford in the Department of Earth and Planetary Sciences. She is a planetary scientist who studies how atmospheres of rocky planets form and evolve, and how they are shaped by geological processes such as plate tectonics, as well as radiation from their host stars. By combining these processes also with models of planetary formation, as well as atmospheric escape, Laura is hoping to understand the evolution of a planet's habitability over time. And that includes not only the exoplanets that we typically observe orbiting other stars, but also our own planets in the early solar system. I also wanted to mention that Laura is a big fan of science fiction. That's why we were playing the Star Trek music as you guys were walking in. And that pairs perfectly with her field of research, which allows her to dream big, but at the same time also exploring the possibility of habitability beyond Earth in a scientifically grounded way. So without further ado, let's welcome Laura. Hold for technical.
Okay, great. Thank you all so much for being here. This is such a great crowd, a great turnout. I'm really honored to be here to tell you today a little bit about some of the strange new worlds that we have been learning about with the James Webb Space Telescope in the past few years. As Zenon said, I am a big fan of science fiction. And when I was a kid, back in, the long ago 1900s, I used to watch a lot of Star Trek: The Next Generation with my dad. And I love this show because, if you're not familiar with the show, as maybe some of our younger audience members might not be, every week, the crew of the Starship Enterprise gets to go on a new adventure somewhere in the Milky Way galaxy, where every week they get to go and see a new planet and get to interact with new alien life forms or new alien civilizations and get to go on these amazing adventures. And the role in the show that really resonated the most with me when I was a kid wasn't really the crew of the Starship Enterprise, although I did kind of want to be Geordi with the visor. But it was the writers that really got to imagine all of these strange and different worlds that look something that are all very different, but also all very similar to our own Earth. And imagine the kinds of planets that might exist with life on them somewhere else in the galaxy. And so I'm really fortunate and privileged that I actually get to do that for my job now. Basically, that is my job. I get to tell stories about how planets form and evolve. So imagine the Earth back when it was first forming and covered in lava and giant impact craters. And how did it turn into the planet that we see today, with its beautiful oceans and clouds and the green continents that we live upon? And my group, we're theorists, so we tell stories about how these planets form and evolve and the processes that go on to make these planets change and become what we see them to be today. And we back those stories up with math and physics and computer programming. But some of the processes that we study, I'm going to talk a little bit or touch a little bit on today. And some of those processes, okay, I'll get to that in a minute. What we see here is that the Earth's atmosphere has evolved over time. The figure on the left is showing something like what the Earth might have looked like right after it formed. It's hot, it's molten, it's covered in lava, and it has a massive atmosphere that's unlike our atmosphere today. It was probably mostly carbon dioxide and water. The planet was probably so hot that all the water that's in the oceans today was actually in the atmosphere as steam. And so this is thousands and thousands of times more carbon dioxide and more water than is in our atmosphere today. And then somehow that planet transformed into our beautiful blue marble covered in oceans with atmosphere that's mostly made out of nitrogen and oxygen, as we see here. And some of the processes that caused this transformation included things like the brightening of the sun over time. The sun was probably about 30% dimmer when the Earth first formed than it is today, and that evolution has caused changes in the climate of the Earth over time. Some of the other processes include impacts that happen during the process of planet formation. These are huge energetic events that probably melted the planet and reset all of the chemistry of the planet that it might have started with. This is a simulation of something like the giant impact that might have formed our moon. As the planet cools and evolves over time, geology is an ongoing process that has happened for 4 billion years on the Earth. And that includes things like volcanoes that take gases that might be trapped in solid form in rocks and bring them back into the atmosphere. Things like carbon dioxide and water vapor, again, bringing those back from the interior of the Earth back into the atmosphere. There's other processes that reverse that take gases out of the atmosphere and put them back into rocks. So this is a process called chemical weathering or carbonation, where you take CO2 out of the atmosphere and you dissolve it into rainwater. And that rainwater interacts with minerals under the surface. It dissolves some of those minerals and reprecipitates others, like the calcium carbonate and bicarbonate that you see in these drippy formations in caves. That's CO2 that's been pulled out of the atmosphere. And the other process, of course, that has altered the Earth's atmosphere is life, especially photosynthetic life, both plants on land and bacteria and phytoplankton in the ocean. Photosynthesis takes carbon dioxide out of the atmosphere and turns it into the oxygen that we breathe as animals. Oxygen hasn't been very abundant in the Earth's atmosphere until about the last 700 million years of our 4.5 billion year lifetime. And that's largely as a result of the evolution of the plants that occupy most of the surface. If we look back at our big, blue, beautiful ball, the atmosphere is important for many aspects of habitability. It protects us from radiation from space. The atmosphere actually warms the surface due to greenhouse effect and keeps the surface nice and comfortable for us. And it allows water to be present as a liquid on the surface. Without the confining pressure of the atmosphere, it would all just eventually evaporate away. So the atmosphere is important for many aspects of habitability. In my research group, we asked a couple of guiding questions that I'm going to talk about throughout this talk. One is just, how unique is Earth in the universe? Are there other planets like this somewhere else that we can find, like those planets that we saw in Star Trek? How important are all of these individual processes that I've talked about in producing a planet that can support life? Right? If we turn the knobs on those processes in different ways and make one more efficient and one less efficient, can we still get a planet that would support life? And can we observe these processes actually happening on other planets? Can we use that, like observing the end state of a planet that has gone through different evolution to test our models, to push them into different directions so that we can understand some of the interdependencies that we don't necessarily get to examine when we're just looking at a single example? So we live in a very fortunate time where now we can actually start to try to do this because we now have a huge population of planets to start to compare to. Back in the 1990s, when Star Trek: The Next Generation ended in 1994, we didn't know of a single exoplanet. The first exoplanet was detected in 1995. An exoplanet is a planet that orbits another star. Very simple. It's sometimes called an extrasolar planet. This is an artist's imagination of what the sky might look like if you could zoom in on each individual star and see how many planets they each had. We have so far discovered more than 6,000 exoplanets in the past 30 years of exoplanet science. And those planets orbit more than 4,500 stars. Many of those systems are multi-planet systems like our own, where there's 3 or 4 or 5 or more planets orbiting the same star. And planets, all exoplanets, planets come in different flavors. We can look at our solar system for guidance in this way. We have 3 different kinds of planets in the solar system. The biggest are the gas giants, like Jupiter with its big, beautiful cloud bands and Saturn with its enormous rings. And they're mostly made out of hydrogen and helium gas, like the sun. And then we have the ice giants that formed in the cold outer reaches of the solar system, Uranus and Neptune. And they're made mostly of things that you probably don't think of as ice. Things like methane and ammonia and nitrogen that were frozen out in the outer reaches where they formed. And then the warmer inner solar system, we have the rocky planets that I'm going to focus on today. These are Mercury, Venus, Earth and Mars, of course. These are mostly made out of rocks with metal at the center that may produce a magnetic field that may have a role in protecting our atmospheres from some of these external influences that I'm going to talk about. But only the Earth, of course, has this layer of liquid water at the surface in our solar system. If we look at the exoplanet population, we've found all those different kinds of planets amongst the exoplanets as well. We have found gas giants, we have found Neptune-sized planets, we have found rocky planets, or terrestrial planets, as it's called here. And then we found a new class of planets that we don't have in the solar system. These are called here super-Earths, but sometimes we call them mini Neptunes also, depending on which one we think those planets are more compositionally similar to. But so we have planets, roughly 2,000 planets, that are similar, at least in structure and density and composition, to the Earth. And we think, based on inference, that, okay, then they might experience the same kind of physics, the same kind of geology, the same kind of processes that affect their atmospheres as the Earth experiences. If we look at the orbital properties of these planets, this diagram is showing us the size of planets on the vertical axis. The color of the planet here is indicating the method that was used to detect it. So it's not super important for our story here. And the horizontal axis here is showing the orbital period of the planet in Earth days. So how long is 1 year of this planet's orbit? If I put Jupiter and Earth on here, you can see that Jupiter up here and Earth down here. Earth is a little bit lonely by itself down here. You can also see this sort of diagonal structure in this planet population here. Right? There are no planets that we have detected out in this region, objects the size of Earth, but at larger orbital periods. And we think this is just an observational bias. It's not that we don't think that there are planets out in this region. It is that they're really hard to detect with the methods that we have available today. And so we think eventually we are going to be able to fill in this population further as we have more time to observe some stars, as we get better and bigger telescopes to observe with. We'll be able to find more planets in this parameter space. But right now, Earth is kind of alone here. But we have found many planets that are roughly the same size as Earth that I've shown highlighted in this box. But what you can see here is that almost all of them are on shorter orbital periods than the Earth. And that usually means that they are actually closer to their stars. The orbital period sort of scales with orbital distance, but it depends a little bit on the mass of the star. So if they're closer to their stars, most of these planets are hotter. Some of them much, much hotter than anything that we have in the solar system. So, well, we want to learn, though, about planets like the Earth, planets that are cooler and temperate. So what can we actually learn about the Earth from these kind of weird, hot planets? Well, as I mentioned, there's lots of processes that go into the habitability and the making and the evolution of a rocky planet. We can kind of categorize all of the factors that go into this by thinking of them as planetary properties, stellar properties, properties of the host star, and properties of the planetary system that that planet finds itself in. All of these things can affect the habitability of a given planet. And amongst these different families, we can find huge numbers of different kinds of variables that all will have some influence on the habitability of that planet. And I don't expect you to digest this diagram. There's a lot of stuff here. And honestly, we don't know all of the different interplays between all of these different processes and all of these different variables and how they all affect the habitability of one particular planet. We only know it for Earth, right? We only have one example. So by looking at these planets that are in these weird parameter spaces where we're sort of, in many of them, we're amping up the stellar light that the planet is receiving, or we are changing the chemistry of the surface and the initial atmosphere, we can test our models by looking at these different parameter spaces, these different ways that these processes might affect a planet's evolution. So let me give you an example in the solar system of a comparative planetology thing. And this is by comparing Earth and Venus. Venus is the sister planet to Earth in the solar system. It is by far the closest analog that we know of anywhere. It is about 90% the size of Earth. It formed in the same solar system. If it orbits the same star, it is not that much farther away from the Earth, or not that far away from the Earth. And yet it ends up very different than the Earth. You can tell just by looking at a photograph of them. But if we look a little deeper at their atmospheric properties, Venus has a really thick atmosphere. It's like 90 times thicker than Earth's atmosphere. And it's mostly made out of carbon dioxide and nitrogen. Maybe sort of similar to what Earth was like 4.5 billion years ago. The surface temperature, because of all this carbon dioxide, it causes a lot of greenhouse warming, and so the surface temperature is extremely hot. It's hotter than most of your ovens can get to, about 870 degrees. If you have a pizza oven, you might be able to get to that temperature. But it has no water. There's no liquid water on the surface of the planet, and there's a teeny tiny little amount of water vapor in the atmosphere, but that's it. In comparison, look at Earth, atmosphere of oxygen and nitrogen affected by biology and covered in oceans with a very nice average surface temperature of around 60 degrees Fahrenheit. Right, so why are they so different? We think that they actually probably formed similar with similar amounts of water. What happened to Venus's water? Well, we think this is the process of evolution, the evolution of this planet's atmosphere. And largely we think what the deciding difference is that Venus is closer to the sun. What happens is that makes Venus a little bit hotter, especially early on when all of the planets are hotter when they first form. And it had a similar amount of water to Earth, but because it was hotter, most of that water was in the atmosphere. And if it's in the atmosphere, it can actually escape from the gravity well of the planet if it's heated up enough by the stellar radiation. So we think that this is largely what happened. The carbon dioxide remained in the atmosphere because it's a heavier molecule, and it's harder to give it enough energy to escape than it is for water vapor to escape. So this is a model that I'm going to show you, walk you through this graph. Each of the points on this graph you can imagine as a simulation of one planet's evolutionary history, where we're looking at the final state of that evolutionary history. And we've started the planets at different orbital distances from the sun, and we have given them different initial water budgets, so different amounts of, I've just called it an ocean. So one ocean is the amount of water Earth has today. And we let it evolve using a model that tracks the escape of water vapor from this planet's atmosphere. And we look at how much water it has left at the end of this evolution. And what we can see is that here is Venus and here is Earth. And Venus is over here on the left with all of these planets, where essentially all of the water has escaped from these planets over their early history. And Earth is over here on the right-hand side of this diagram, where they have largely kept almost all of the initial water that they started with. So there seems to be some critical distance, at least for planets that are orbiting the sun, where if they are closer to that star than that distance, they're going to lose all the water that they might have started with. Is this something that we can test with other planets? Well, this is also related to the concept of the habitable zone. The habitable zone is this imaginary region around a star where we think that a planet could potentially have the right conditions to have liquid water on its surface. Did I qualify that enough? This region is a model for how we understand the atmospheric conditions on the inner and outer edge. And so a planet can be in this region and not have water just because it never got it to start with. But if it did get water to start with, that water will be happy and it will remain on the surface. But if it is too close to the star like Venus, then maybe it loses all of that water in this region what we've labeled too hot. Planets further out are too cold. like Mars, and if they have water, that water is probably frozen at the surface. And so that's usually not thought to be very conducive to biology or biochemistry happening. So this habitable zone, again, is a model. And for the solar system, we kind of know where those boundaries are. The inner boundary seems to be around where Venus is today, and the outer boundary seems to be around where Mars is. But what about for other stars? It turns out other stars can evolve differently than the sun. And in fact, smaller stars than the sun evolve actually in a more extreme way than our sun does. The brightness of our sun is relatively stable and constant over time. This diagram, which was made by my lovely husband at the back of the room, is showing how the habitable zone boundaries evolve for stars of different sizes. And what you can see is that Earth is up there in that quadrant, and Earth remains more or less in the habitable zone of the sun for this entire simulation. This is showing time evolution of the habitable zone. Whereas if we look down here at these small planets, our closest neighbor is Proxima Centauri, and we believe that there is a planet in the habitable zone of this star. But if you see, it is actually in that too hot region for most of that early history. So these stars, these small stars where we've found a lot of planets we can actually observe, seem to have a worse problem here, where some of these planets that might look like they could potentially be habitable today, maybe they went through this extreme early history and they actually aren't habitable because they lost all of their water, these small stars. So this is a danger zone. And so we have to be wary of looking at planets in this particular region and assess whether or not they have lost their atmospheres or at least their oceans. Now, it turns out this model was relatively early in understanding the effect of atmospheric escape on exoplanets. And we actually think the problem might be even more extreme. So Venus, as I mentioned, has retained a pretty thick atmosphere of carbon dioxide because it didn't receive enough damaging radiation from the sun to lose all of that carbon dioxide, which is very heavy. It just lost the lighter water vapor. But we think that many of these planets that we have found might be actually so close to their stars that they could lose everything. All of the carbon dioxide, all of the nitrogen, anything that they might have that would be a gas, we think they might lose it. This is a model where we're just looking at the amount of radiation the planet is receiving over its lifetime. This is the total high energy radiation that planet receives. And we're sort of plotting it versus the gravity of the planet. The gravity of a planet, if it's higher, a planet can hold on to its gas more tightly, and it will take more energy to make it escape. So bigger planets can hold on to atmospheres a little bit more easily than smaller planets. And what we've found empirically in the solar system is that there seems to be a dividing line between planets that have atmospheres and planets that don't have atmospheres. And that is this line here called the cosmic shoreline, where we think planets that are below that line are likely to keep their atmospheres, all of it, or at least some of it. Of course, we think Venus has lost some of its atmosphere, but not all of it. Whereas Mercury, up here, we know doesn't have an atmosphere, right? And on here, I've also plotted in orange the rocky exoplanets that we know of today that are potentially observable. And unfortunately, you can see that most of them are lying above that line in that region where empirically, we think they might not have atmospheres. So we have to now go and test this model. And how do we go about testing this model? Well, we need to go and try to observe the atmospheres of these small planets. Now that turns out to be an extremely challenging problem. A small planet has a small atmosphere, and it has a small signal relative to the size of its star. Prior to, or up until recently, the two best telescopes we had for this were the Spitzer Space Telescope and the Hubble Space Telescope. Spitzer was a relatively small telescope. It was an infrared telescope that looked at sort of longer wavelengths than Hubble looks at. And these two telescopes operated and were able to observe some exoplanets. Spitzer is small enough that it really kind of struggles with very small planets. And at the time that we started actually detecting small planets that could be observable, Spitzer had actually gone into a more limited mode of operation, where it wasn't able to access most of the wavelength range that it had used to been able to observe in. And the detectability of a small signal actually scales with the size of a telescope's mirror. That's why I'm showing this here. The smaller the signal you want to detect, the bigger the mirror you need. Astronomers often call their telescopes light buckets. You need a bigger bucket to catch more photons from a fainter target. And so along came the James Webb Space Telescope. You can see the size of the mirror in comparison to Spitzer and Hubble is much, much larger. It is much more capable of looking at these small planets than any of these previous telescopes. Observing these planets from the ground is really not very possible with the current suite of telescopes that we have, although in the future with extremely large telescopes, it might be possible to observe a few. James Webb launched in 2021, shortly after the Spitzer Space Telescope went offline. It launched on Christmas Eve in 2021, after several decades of development and delays. And as you might imagine, it was a very tense holiday season for the astronomers who were waiting anxiously to find out if the launch was successful, if the deployment was successful, if the orbit insertion was successful. And all of them were, of course, right? Very successful, and James Webb has been operating admirably for the last 5 years. Actually, if you want to hear more about the instruments and the operation of the telescope, I encourage you to go and look at Bruce McIntosh's talk that is on the KIPAC YouTube page from 2023, where he's an instrumentalist, and he can tell you a lot more about the operation of this telescope. But James Webb has really been working wonders for small planets. It has really started to revolutionize, and we're really just in the beginnings of these sets of observations. We're in year 5 right now of active observations with James Webb. And the kinds of observations Webb is taking, I'm going to talk about 2 different kinds. So the first is one of the methods by which we can actually detect an exoplanet, and this is called the transit. So imagine you are the observer and I am the star, and when a planet passes between us, you can observe the shadow of that planet on the star. And so this is an actual set of photographs of a real transit. Does anybody recognize what this is? Maybe you saw it yourself. This has happened in 2019. This is the transit of Venus in front of the sun. It is a pretty rare event for us to be able to observe from Earth. It only happens about every 80 years or so. But what you can see here is that the Venus is casting a shadow on the sun. If we're monitoring the brightness of the star over time, then we can see that shadow as the planet moves in front of the star, and then the shadow goes away as the planet moves back out of transit. The other kind of observation we can make is when the planet goes behind the star, and this is called a secondary eclipse. And here what we're losing is actually the light from the planet itself. And so this is really an effective technique for hot planets, which themselves are emitting enough radiation for us to be able to detect. And a hotter planet is going to produce a bigger signal in secondary eclipse. This is just showing an example of sort of what the light curve of a transit and secondary eclipse of what a full orbit would look like. If we average the star's brightness when the planet is in neither of those positions, then when a transit happens, we get a relatively deep dip because we're losing the light from the star. And when the planet goes behind the star, we get a much smaller dip because we're only losing the light from the planet itself. Okay. So during both of these processes, we can actually detect the planet's atmosphere. During transit, This is a technique called transit spectroscopy. Some of the light from the star is actually filtering through the planet's atmosphere, which is at least partially transparent to that light. And the atmospheric gases of the planet's atmosphere absorb certain wavelengths of light, depending on which gases are present. And they basically leave their fingerprints on the signal. And because the fingerprint of each gas is unique, we can use that to measure the composition of a planet's atmosphere. The other method that we're going to use to talk about rocky exoplanet atmospheres is that secondary eclipse. And this is a program that has one of the largest programs on JWST, which has been specifically designed to test this model of the cosmic shoreline. And essentially what it gives us is effectively a yes or no answer to the question of, does this planet have an atmosphere or not? And it relies on secondary eclipse. And here is how it works in sort of broad strokes. Let's take the example of Mercury and Venus in our solar system. Mercury, no atmosphere. Venus has a relatively thick atmosphere. Mercury has a huge temperature contrast between the day side, which is detectable during secondary eclipse, and the night side, which is detectable during transit. It is almost more than 1,000-degree difference in temperature between day and night on Mercury. If we look instead at Venus, Venus essentially has the same temperature across the entire planet. And the reason for that is the atmosphere. The atmosphere takes energy that the sun deposits on the day side, and it moves it around to the night side, where it sort of evens out the temperature on the surface. And so, because the secondary eclipse is sensitive to the temperature of the planet, what we find is that planets that have atmospheres will have a cooler temperature than we expected because they're moving energy around to their night side. And this is testable by secondary eclipse. So again, I'm going to show you a couple of results in a moment that show us that we can say, yes, this planet has an atmosphere, or no, it doesn't, with this method. I'm going to give you sort of 3 examples of observations that JWST has been able to take so far. I'm going to show you where the planets fall on this cosmic shoreline plot. This is basically the same as the black plot from previously. But here what it's showing is all of these planets in color are planets that have either been observed or will be observed by JWST. And the color tells you what kind of observation will be taken. So the first set of planets we're going to talk about are the TRAPPIST-1 systems. I'm going to go from cooler planets up to warmer planets as we talk about these. So the TRAPPIST-1 system, if you follow exoplanets at all, you may have heard of the TRAPPIST-1 system. It is the closest planetary system to us. It has 7 planets. Most of them are roughly Earth size. This is a physical comparison of that system, where you can see in other aspects, it is very different than the solar system. This is the physical size of the system, and here it is in comparison to our entire inner solar system. It occupies this tiny little region here. The star is here. I don't know if you can see the dashed outline around that star. But that is the size, the physical size of our sun. This star is tiny. And it is actually much more comparable to Jupiter and the Galilean moon system than it is in size to our own system. But these planets, there are 3 that are in the habitable zone. They have roughly similar temperatures to some of the solar system planets. And again, these planets are actually amongst the most detectable of the rocky planets we know of. So the first 2 planets that JWST actually observed were TRAPPIST-1b and TRAPPIST-1c. And it observed those planets in secondary eclipse. So we're trying to measure the temperature of the day side. I should say that I was involved in the observations of TRAPPIST-1c. What I contributed was a model for trying to understand how this planet's atmosphere might have evolved. And this is a result of some of those models. Our model actually predicted that TRAPPIST-1c should have an atmosphere. Should have an atmosphere somewhere between the size of Mars and Venus. The color here are contours for predicted atmospheric pressures. The vertical axis is the initial size of the ocean that we gave our model planets. And the horizontal axis here is the amount of high energy radiation this planet would have received over its lifetime. So all of our model results suggested that this planet should have an atmosphere. And what did we find? Well, here's from secondary eclipse, we essentially got one data point at one wavelength for this planet, for this first initial set of observations. And it's at a wavelength that is sensitive to absorption from carbon dioxide, which we think is a major gas in many planet atmospheres. And what we could rule out was that there was definitely not a thick atmosphere on this planet. The red and yellow curves here would be atmospheres that are somewhere around in between the size of Earth and Venus's atmospheres. We could definitely rule those out. The two models, though, that both seem to match this observation is this purple line, which is consistent with a thin atmosphere, about 1/10 of the pressure of Earth's atmosphere with a little bit of carbon dioxide. So consistent with our models. And the black one down here is unfortunately a model that is consistent with a bare rock that we're seeing straight down to the surface, that there's no atmosphere on this planet. So this set of observations, unfortunately, on its own, is inconclusive. We can't say for sure whether TRAPPIST-1c has an atmosphere or not, although I'm leaning towards a little tiny atmosphere. This is transit spectroscopy of that same planet. The black points are observations with JWST, and the colored lines are, again, models that we're comparing to for atmospheres of different compositions. And unfortunately, again, this data is a little bit inconclusive. You can see that this is a really challenging set of observations. We have really good data, but the error bars are still big enough that we can't distinguish between these atmosphere scenarios right now. So with more data, we might be able to drive down the signal to noise here and improve the fit. And maybe eventually we might be able to determine what kind of atmosphere this planet has. But I'm suspecting it's a relatively thin atmosphere. So moving on from this one, that was the coolest planet we're going to look at. The next planet we're going to look at is this LHS 3844b. This is hotter than the TRAPPIST-1 system. This diagram is showing essentially the detectability of the planet in comparison to other planets of similar sizes. There's TRAPPIST-1b and c, these two objects here, and the size of these symbols are related to the size of the signal we expect for the planet. It's relatively large for a rocky planet. But this planet has a temperature that is much higher, around 800 degrees, in comparison to 200 or 300 degrees for the TRAPPIST-1 planets. And this planet was actually one of the few planets that we managed to observe with Spitzer back before it was decommissioned in 2019. And what we got was a secondary eclipse measurement that gave us a definite temperature for the day side of this planet, which was very hot. It was about 1200 degrees, and we constrained the night side temperature to be very cold, essentially equivalent to being exposed to space. So this is an actual temperature map of this planet. And so we think this planet probably doesn't have an atmosphere. Shocking. This is consistent with our cosmic shoreline model. But we did go and measure it with JWST. And why did we go and measure it with JWST? It was because we can actually see the surface. So here's the one Spitzer data point in blue. These other colored points are observations with JWST, and we can actually rule out certain compositions for the surface of this planet, which is not something I thought I would ever be able to say, to be honest. It's hard enough to do this in the solar system for asteroids, much less to do this for a planet that's several light years away from us. But what we can rule out, we can definitely rule out this green model, which is a composition similar to granite, like you would find in Yosemite. The mountains of Yosemite are made of granite. Instead, what the surface looks like is these yellow or blue models. And those are essentially rocks like you would get out of a lava flow from the Hawaiian island volcanoes. These are basalts. They're very dark rocks. And this, you can't even hardly see it. This is an artist's imagination of what this planet looks like. It's black. Take my word for it. It's a black planet. Okay, the last planet I want to talk about is the hottest. And in fact, this is one of the hottest planets we know of. And this is 55 Cancri E. It is so hot that NASA made a travel poster out of it that dubbed it the lava world. It has a temperature of about 2,000 degrees Kelvin. For reference, rocks melt at about 1,200 degrees and they start to vaporize around 1,500 degrees. So this is hot enough to vaporize the very surface of this planet. And one of the very interesting things about this planet is that it has shown variability. These are secondary eclipse observations with JWST, this sort of square-shaped thing in the middle. You can see sometimes it's shallow, sometimes it's not there, and sometimes it's deeper. And we think this variability, it's something that's happening on the planet. We're not sure what. Maybe it's volcanism. Maybe it's clouds that are coming in and out of view. We're still not sure yet. But we do think this planet, of all of these planets, has an atmosphere. This is additional JWST observations. Again, comparing two colored models of the planet's atmosphere. We think this planet has an atmosphere made mostly out of carbon-rich gases, like carbon dioxide, which is common in the solar system, or carbon monoxide with a single oxygen, which is not common here. It's a product of high temperature processes. And so looking at the results in sum for the cosmic shoreline model, I want to finish here by looking at some of the results for other planets that we haven't been able to talk about in detail. What I told you was that with secondary eclipse, we could tell whether a planet has an atmosphere based on the temperature of its day side in comparison to the maximum possible temperature it could have. If I plot them on this diagram, if they are in this pink region, we expect these planets to be bare rocks, to have no atmosphere. If they're in this blue region, they might have a thin atmosphere, or down here, they might have very thick atmospheres. So this cosmic shoreline model suggests that it would be the coolest planets down here that might have signals of atmospheres. So we should expect the cooler planets to plot down here, and the hotter planets to plot up here in the pink region, where there's bare rocks. So what did we actually find? It's very different, right, than what I just said. We have this little hint. The TRAPPIST-1 planets down here might be entering this regime of planets that have survived the XUV radiation from their star and maintained an atmosphere. These planets in the middle, they seem to match the cosmic shoreline. They don't seem to have atmospheres at these intermediate temperatures. These hot guys, like 55 Cancri E, these are the ones we have found that seem to have big, thick atmospheres. And so I don't have an answer for you. This is brand new observations within the last year or so. We don't have models that can explain this behavior yet. We don't know why those planets have atmospheres. And I think that is actually really cool and exciting as a person who tries to model how these planets work. So what this tells me is that our models are missing something. We're missing some physics or some chemistry or some process that we don't know about because it's not that important on the Earth or Venus. And so I think we can learn a lot of things about rocky planets from looking at these planets. Coming back to our guiding questions, how unique is Earth in the universe so far? Very unique. We have no other examples anywhere near it. But I think we'll get there eventually. JWST is going to struggle to work on the cooler planets. It'll have to be the next generation of space telescope, maybe the Habitable Worlds Observatory, that might be able to actually probe planets as cool and as lifelike as Earth. But we've definitely learned more about the processes that are operating. And we are going to continue to learn more as JWST fills in this parameter space of small rocky planets as we learn more about all these hot planets and try to understand why they are defying our models. So with that, I think I'm going to end here since I'm out of time. But I would love to take your questions.
Awesome. Thank you so much, Laura, for a very informative and packed with exciting information. So we're going to start the Q&A. Feel free to just raise your hand. I'm going to repeat the question for our online audience. All right, great. And over there.
Maybe you mentioned it. I'd like to know whether you're planning to use coronagraph telescopes in your research.
Yeah, coronagraph telescopes. Coronagraph telescopes are able, sorry, Zenon, you were going to repeat the question.
Yeah. Sorry. The question was, how do you use the coronagraphs in your current research? And maybe you could also explain what coronagraph is.
Sure, yes. A coronagraph allows us basically to block out the central star in a system and actually take a direct picture of the planetary system itself. In fact, I probably have a figure here showing, oh, no, okay, all right. It's fine, don't worry. So we can use them in the future potentially to take an actual image of an Earth-like planet. Right now, JWST has this ability to do this, but mostly for planets that are pretty far away from their stars. And so that is going to limit us right now to gas giant planets, and especially young gas giant planets that are really hot. So the future observatory that the US is currently working towards planning is Habitable Worlds Observatory, which will be a coronagraph, will have a lot of coronagraph instruments. And it is being specifically designed so that we can actually directly image a habitable world. So yes, in future, I hope to use them a lot.
And there's actually a perfect follow-up question asking, you talked about the Habitable World Observatory. Can you maybe say a little bit about, like how that is going to advance, what it is going to provide that JWST cannot?
Yeah, so as I said, JWST is really going to struggle to observe the small planets that are further away from their stars, that are cooler. We've seen some of these limitations already. So all of the planets that we have been able to observe that are relatively cool are around these small stars, these stars that seem to be the most damaging to the planet's atmosphere. In order to find a planet that can actually retain its atmosphere, we need to go to larger stars like the sun that are less damaging overall to the planet's atmosphere. And in order to do that, the signal size for those planets is so small because it scales with the size or inversely to the size of the star that we do need to go to other techniques and use things like coronagraphs to be able to directly probe those atmospheres.
That's very cool. All right, I have a hand over here.
Hi. Given what you just said, that the James Webb Telescope struggles to see cooler planets that are small but far from their stars, is it possible that the correlation that larger, hotter planets are more likely to have atmospheres just comes from that and not the data?
Not necessarily. So we know that there are plenty of gas giants around these small stars, around some smaller stars, and they all have atmospheres. So we think that it is this correlation. One of the things I did mention is that these smaller stars also have a higher proportion of the really damaging radiation like X-rays and ultraviolet, especially early in their history. And they just have a lot more activity. And in order for planets to be habitable, they have to be extremely close to their stars because those stars are so small. So we don't think that there is a direct correlation between atmosphere retention and necessarily the temperature of the planet. There is a stellar effect there that we have to consider as well.
Yeah, all right. Oh, here.
A different telescope to see the planets?
Oh, great. Yeah, that was a great question. Can you send a different telescope to observe all these planets?
Yes, we're gonna try to. Unfortunately, well, the next telescope is probably gonna be ready about when you're ready to use it, I think. And we will have a lot of upcoming very large telescopes on the ground that are also going to be able to do this. Again, those are probably going to be ready about when you're ready to use them.
And a follow-up question from online asking, well, you are talking about future facilities. So how is the Vera C. Rubin telescope is going to aid, or will it aid the search for exoplanets in any way?
Yeah, the Rubin telescope. The Rubin telescope is a large telescope that KIPAC and SLAC have had a big leading role in. It is one of these large ground-based telescopes that's doing this crazy all-sky survey where it's taking literally terabytes of data every night about the whole sky. It's really crazy and amazing. And I think one of the things that it's going to help us do is actually find the targets, the planets that we want to look at with the upcoming HWO telescope, the Habitable Worlds telescopes. Right now, we don't actually, remember Earth was lonely on that plot of planets versus orbital period. We still need to find the targets that HWO wants to look at. And I think Rubin is going to help with that.
Yeah, that's really great that different kind of facilities, they complement each other.
That's
one
right.
is kind of doing wide surveys, picking up the targets, and the other one doing more in-depth studies of them. Yeah, awesome. Okay, another hand over there.
Yeah, first of all, thank you for a great lecture. I wanted to ask if probes like the Europa Clipper and other research into polar bodies that may harbor ocean in our solar system, like Titan, can help fuel models that might help with the search for cooler exoplanets with atmosphere, and how those two might correlate.
Yeah, that's a great question. So the question was whether any of the probes like the Europa Clipper that tries to study our own solar system planets may actually help with modeling of the exoplanets, either their formation or their atmosphere, and how that informs of, in your research.
Yeah, so if you don't know, Europa Clipper is a NASA spacecraft that is going to go to one of Jupiter's moons, Europa, which is a great big icy moon covered in ice, but with an ocean underneath of it. And one of its goals is to probe the surface of the ocean, of the ice, and try to see if there are any organic compounds present that might be indicative of life there, probe the thickness of the ice shell and see how deep we have to go down to get to the ocean. And things like that. So Europa Clipper is going to tell us a lot about the environment of icy moons, which is a very different model of potentially habitable environments than what I've been talking about. With exoplanets, we're largely stuck trying to find planets that are habitable where the life forms have affected the atmosphere in a measurable way that we can detect. For us, studying exoplanets, icy moons are probably a little out of reach in terms of thinking about habitability, at least in the near future. And that is where all of the solar system science really excels in trying to find really different kinds of habitable regions. And of course, anything we learn about habitability is going to help us improve our model, because again, right now we have one example. It's really hard to build a model you can extrapolate from one example.
Absolutely. Great. I am good. Okay, so over there, the hand, yeah, at the back. Great question. Okay, so the question was, do you think there is a possibility at all that other life forms in the universe, they do not depend on water at all? And if not, then why are we even searching for water?
Sure. I remember one of my favorite episodes of Star Trek Next Generation was about a silicon-based life form. And I think it's really fantastic to try to think out of the box like that. Unfortunately, all the biologists tell me that really the best option that we know of for chemistry, for biochemistry, all the reactions that we think had to go into creating the life that exists on Earth, they all had to involve water and carbon and hydrogen and nitrogen and a certain subset of elements. And unfortunately, right now, there's very possible that there are other life forms that use different kinds of elements and different kind of solvents and different kind of chemistry, but we don't know how to look for that, right? Right now, we're trying to, right now we have like an infinite parameter space, and we're trying to constrain it and say, okay, these are the planets we should focus on because we're pretty sure this kind of life, we know it works, right? It works here at least. And so that's why we're focused on water.
Great. And actually, a relevant question from online from Tiara asking, will you be able to eventually see if there are life forms on those planets that have very similar environments like Earth? And if so, how are we even going to see it? Is it through like spectroscopy? Are there going to be like biosignatures?
Exactly, yes. So what we will be looking for is something called a biosignature. This is some product of the biochemistry of the planet that sticks out to us. On Earth, that is oxygen in our atmosphere. Oxygen wouldn't be there without photosynthesis. It's a highly reactive gas. It would, if biology shut off today, oxygen would be gone in a few million years. It just wouldn't be there. And so for us, for Earth, that is the smoking gun, that there is biology on the surface of the Earth. That plus the fact that the continents are green. If you could see the continents and see that they were green, that would also be an interesting interesting biosignature. So what we try to imagine, because we do try to think out of the box and try to think how would other biochemistries affect the atmospheres of their planets. And so one of the things we think it would be a strong biosignature would be gases that are out of equilibrium with our atmosphere, that are strong signatures that something with energy is driving the system away from the natural state that it wants to be, being driven by the natural planetary processes. So there's a lot of modeling work that is going on, that has gone on, that will continue to go on for many decades as we try to improve our understanding of this problem. What is it that we need to be able to observe in order to see an atmosphere? So we're going to look for gases that don't seem like they should be there. And to do that, we'll have to do it with spectroscopy. We'll have to be able to measure the composition of the planet's atmosphere directly in a way that we're still finding challenging today. And that is where the HWO telescope and these extremely large ground-based telescopes are going to come in. They'll be able to do that kind of measurement of these planets' atmospheres.
Great, yeah. And we'll take one more in-person question. Over here, is that a question?
Gases that should not be there, but how do you know for every planet what gases should be there?
Great question.
Yes.
This is a modeler's dream. You get to make all the models.
Yeah, do you want to repeat the question?
Yes, yeah, sorry.
Oh, yeah. So the question was, you mentioned you're looking for gases that are not supposed to be there, but then how do you even set the baseline as to what gases should be there in the first place?
Yeah, so some of the processes that we look at for that are how is the geology affecting the chemistry of an atmosphere? How is the solar radiation affecting the atmosphere? Things like photochemistry. In Earth's atmosphere, photochemistry, photons from the sun basically create the ozone that's in our upper atmosphere. So we have models that we have developed that do a really good job on predicting that kind of chemistry in Earth's atmosphere. We've pushed them so that they can do the same kind of thing for Mars and Venus. And so what we would do is try to measure the composition of that atmosphere and then plug it into as many models as we could find that model the chemistry of that atmosphere and see, do those models predict that you should expect that kind of gas there? And so that's kind of how we would go about it. But yeah, I think one of the things that as a field we're already starting to wrestle with is how do you prove a gas is a biosignature and not just something we haven't thought of that's not in our models yet. Right, so it's going to take a lot of really hard work for us to prove a biosignature when we first find one. And I think the field as a whole is going to be really cautious about it. So it might actually just trickle out a little bit slowly over time before we become really certain. But we do want to be really certain before we blare the trumpets.
Yeah, sounds like sometimes there are more questions than answers.
That's right.
Yes. Great. In the interest of time, we are going to stop the Q&A here, but all of you in person, you're more than welcome to, after the event, directly talk to Dr. Professor Schaefer, and she will be here until the last question is addressed. Okay. Yes, let's give her another round of applause. Awesome. So before we wrap up the event, I just wanted to give a quick overview of what is coming up next. So as some of you may already know, we are continuing this local engagement with Rubin Science. And our next lecture is going to be in August, so Saturday, August the 29th at the Chabot Space and Science Center. And that is in partnership with the East Bay Astronomical Society. So the topic will actually be about how are we going about to study the varying sky and transient objects with Rubin in the era of big data. And other than that, we are going to take a very short break in August and September for our regular programming and come back very strong in the fall quarter with more hybrid public lectures as well as in-person stargazing nights at the Student Observatory. So if you want to keep up with what's new with KIPAC or kind of just want to know what is happening next, so you're more than welcome to follow us on social media or sign up for our mailing list so you will get notified as soon as we have a new event scheduled. So thank you everyone for joining tonight. We will bring everybody back to the screen to say goodbye. Tomorrow we will follow up with an email with all the information that have been shared here tonight, along with a short survey. We absolutely value your feedback as to how the event went tonight and what other topics you would like to hear in the future. So thank you again for joining us tonight, and we hope